Yeah.
Well, Mr. Bryce has one.
What?
Mr. Bryce has one.
Oh, yeah. Does he?
Yeah. I've used it every now and then.
Oh, yeah, he does. It's audio. It's well, and then he writes.
Yes.
Yeah.
This is him on the smart board. Or not the smart board, but like just a pad, a word pad, I guess.
Okay, do you have any homework questions? Anything you'd like to go over before we start today?
21 on page 58.
Says, find the value of C such that the point AB lies on the graph of the function f. Okay, so they give me f of x is 2x squared minus 4x plus c. And they say the point is 1/5. So if 1/5 satisfies it, that means that the y would be 5, so f of x would be 5, and then I could plug 1 everywhere there's an x. And then I could solve for c. So that would be what was 2 minus 4. So if I add 2, would c be 7? That do it? Okay. So if I put a 7 up here in the original, if I place 1 in there, 2 minus 4 is negative 2, plus 7 is 5. That would work. Okay. Good.
Number 17.
17, same page?
Mhm.
Okay. 17 says determine whether the point lies on the graph. Okay, so they give us g of x is square root of x squared minus 1. Is that right? And the point is 2 square root of 3. If I let x be 2, if I put 2 here, what is y?
They're just plugged in.
Yes. So in other words, if I put 2 in and I get square root of 3, that point would be valid. That's good. Probably it's all in the way they asked that question, right? Any other concerns?
61.
61. Sixty-one says the volume of a spherical cancerous tumor is given by V of R equals 4/3 power cubed. R is the radius of the tumor in centimeters. By what factor is the volume of the tumor increased if the radius is doubled? All they want you to do here is replace R with 2R and see how that affects the whole value. So if I put 2R for R, V of 2R, 4/3 pi 2R cubed. What is 2 cubed?
8.
8. Good. So that would be 4/3 pi R cubed times an additional factor of 8, right? So that's how it's affected. The volume would be multiplied by 8 if you double the radius. Multiply by 8. Because of that 2 cubed that's sort of added in there. Okay? So it would be 8 times the original. Any other concerns? Those are good. Very good. I don't know if you feel good or stressed out about the quiz today, but I made a decision that since it's all review material, I'm giving it as a take-home due next Wednesday when we come back. Because I don't want to take class time to have you struggle on that quiz. I would rather do new notes. And I know if I did new notes now, you're going to be thinking about that quiz the whole period. So don't expect that later. But this is review quiz. And I'm going to let you take it home and have that week to do it, turn it in next Wednesday after a holiday. And I'll grade it. There are 3 different forms of this that I have, so be aware of that if you're, don't, in other words, don't compare answers because they're 3 different. All right. So I'm going to go ahead and hand this out. You can put it away, but this will be due on Wednesday when we get back.
You guys showed up.
I wouldn't forget you. Okay, hopefully that's exactly what you were expecting to be on the quiz, but I just didn't want to take the time out of class to do it because toward the end we start to have to rush when we get to integrals, and maybe if we just get through some more sections now, we don't have to rush at the end. So that would make us all happy. All right. So just don't forget to bring that back. And when you sign your name to it, I assume that means I did not get help on it. I did my own work. So. Okay. I want to pick up where we left off last time. I think we had finished 2.2 and we started 2.3, didn't we? We had done 2.2 on combinations of functions and composite functions, composition. We had started the first few of 2.3, and then I told you before we did number 18, I wanted to give you some definitions, and that's where we'll start on page 85. Okay. These, I think, are sort of big for this first unit, as opposed with relation to applications. Some of you will be familiar with what we do here, but if you've not seen it before, let's define what a cost function is. Cost, revenue, and profit, okay, and how they're related. Cost function C of X is the total cost of producing X units, okay? Basically, it's made up of two components, the variable costs and the fixed costs. V of X plus F of X. The easier way to think of the cost function, though, is this way. Little cx plus f. Little c is the cost per unit times the number of units plus the fixed cost. That's the way you could set up the cost function if you're given a word problem. Cost per unit times number of units x plus the fixed cost. And I've tried to define what these are. Whoops. There we go. It's being very sensitive, isn't it? Let's see. Variable cost, V of X, costs that depend on the number of items produced, materials, labor, transportation, etc. All right? That's where the little CX comes in. Cost per unit times number of units. And then the fixed cost is, right there, costs that occur even if no items are produced, like if you have to rent a building, pay salaries, buy machinery at the beginning, and everything. So even if you make no items, you have to pay that F amount, the fixed cost. Okay? So if we simultaneously were to start working number 18 on page 85, let's start with the cost function. Look what 18 says. A manufacturer has a monthly fixed cost of $100,000 and a production cost of $14 for each unit produced. Part A says, what's the cost function? C of X is equal to, well, if we use that formula, we could plug right in. Cost per unit, it said, was what? 14x, and the fixed cost, 100,000. And that's your cost function. Nice. Part B says, what's the revenue function? Let's define that. If I try, move that up slowly, let's see. Oh, it's just not behaving. Just not behaving. What's wrong with it? Well, there we go. The total money, R of X, the total money received from selling X units of the product. Okay? The revenue function R of X is equal little s times X, where S is the selling price per unit. All right? So very simple equation for the revenue function. Selling price times number of units. Total money received. So if they say, what's the revenue function for number 18? They tell me at the end of that statement, the product sells for $20 a unit. So what's R of X? $20. Okay. And then part C is going to say, what's the profit function? Definition of profit function, if I can get it up there. Nice. Total profit received from selling X units of the product. The way we get profit is the revenue minus the cost. The money we bring in minus what we spend. And that would be your profit. All right? So for number 18, to form the profit function, P of X would equal R of X minus C of X. So that's going to be what? 20x
14x plus 100,000.
plus 100,000. The biggest mistake people make on this is they forget to distribute their negative. So if you distribute your negative, the profit function becomes 20x minus 14x, which is 6x, right? And then that negative distributes to the 100,000. So P of X would be, all right, cost, revenue, and profit. Then in part D, I won't make you do both parts, but it says compute the profit or loss corresponding to production levels of 12,000 and 20,000 units. Well, just try 12,000. For part D, what is the cost for 12,000 units? That would be 14 times 12,000 plus 100,000.
1,680,000.
Total?
No, that's just the cost.
Okay, so this whole thing is 600, say it again, 600,
1,680,000.
Thank
you. Yeah, plus.
Okay.
Then you gotta add the 100,000.
oh, and add the 100,000, so that would be 17. 17. Okay. Is that good? Is that what you said? Okay. So that would be the cost for 12,000. What about the revenue? 12,000 would be 20 times 12,000. 12,000. Okay. Well, 20 times 12,000, 240,000. Sorry. Correct. So we're going to have a little difference there. Let me see my calculator here. We said,
I didn't get that top number that he got.
is it one, it's two,
I got
Two-
268,000.
that's what I was checking that, yeah. Okay. So if we do that, it was 168 plus 100, is that right? So 268. Good. Yeah, I thought those are a little far off from each other.
And then I got, when you did the product or whatever, it was negative 28,000.
Ah, that's it. So then when we do the profit, P of 12,000 would be revenue minus cost, so 240 minus 268. So what's actually happened? If
The
they make
loss of 28,000?
a loss of 28,000, that's good. So they actually didn't bring in as much money as they spent, so they lost 28,000. Mostly what they're going to ask us, and they didn't ask me on this question, but I'm going to go ahead and ask it. What if I said, what's the break-even point where they don't make a profit but they don't lose money? When is the profit zero? Well, let's see. Yeah, let's see how many units. And that's a definition I'll give you. The break-even point right down there, if I can move it up just a little. Oh. When is the revenue equal to the cost? This is just, I never.
Something's down in
Yeah,
the
it
word.
seems like it's got like auto scroll.
Yeah, I don't like it. Let's see. Okay. Break-even point, production level X at which the revenue is equal to the cost, or the production level at which the profit is zero. Another way to say that. So you could do that either way. You could set the revenue function equal to the cost function and solve for X, or set the profit to zero. So for this one, if I asked you for the break-even point, we would say what? We would say, the easiest thing to say would be set the profit equal to zero, right? If I said 6x minus 100,000 equals 0. So 6x would equal 100,000. What happens when you divide by 6?
X equals 16,666.
In 2/3? Okay. So that means if they sell, I guess you'd say if they sell 16,666 or 16,667, if you round it up, They would not make a profit, but they wouldn't lose money. So that would be the break-even point. Okay. So do you think, not on the one I just handed you, but on the next quiz, if I described some information like that, could you find the cost function, the revenue function, and the profit function, and the break-even point maybe? That'll be a big one for us in this unit. Okay. But that's a good basic example of it, I think. What you're going to notice past 18, do you see from 19 all the way to 35, all they give you are some functions within the problem, and they want you to plug in a certain value they give and just evaluate it. So, for instance, do you see number 34? They give you that function S of t. They say, what were the worldwide flash memory chip sales in 2002? Well, that's when t is 0. You would just plug a t of 0 in there and you would get your answer for A. That's all those are up to 35. They give you a function and you plug in a value. And I'll assign a few of those, but I don't think they're worth spending your time on. If any of them give you trouble, you'll let me know. The other type I wanted to mention, past the cost, profit, and revenue, break even, are the supply and demand questions. Before we do that one, though, let's do one that I thought was a good linear function problem. Before we do supply and demand. I think 42b is worth looking at. 42b. Okay. 42 says, entomologists have discovered that a linear relationship exists between the number of chirps by crickets of a certain species and the air temperature. When the temperature is 70 degrees, the crickets chirp at the rate of 120 times per minute. When the temperature is 80, they chirp at the rate of 160 times a minute. Part B says find n as a function of t. N is a function of t. All right? If I'm trying to form two ordered pairs, this is like n of t, that would be, t would be my x variable, right? And n would be my y. Would you agree with that? Okay. So that means, what two ordered pairs would I set up if they're t comma n?
70, 120.
70 degrees, 120 chirps per minute, and 80, 160. Once we have those two ordered pairs set up like that, we can find the slope of the equation. Would you agree? What would the slope would be? 160 minus 120, 80 minus 70. Yeah, you said 4, right? Good. The slope is 4. How would you interpret that? If that slope is 4 over 1?
For each degree.
It rises
There are 4
forward.
chirps per minute.
4 chirps per degree increase. So for each degree increase, the 4 chirps per degree increase. Okay. Change in y over change in x. Good. And then if I wrote the equation, y minus y1 equals the slope times x minus x1. If I add 120, what do you say?
160.
160 or minus 160.
Negative would dominate. So that would be good. And I guess to make it official, we could say the number of chirps equals 4 times the temperature minus 160, right? Would that do it? Okay. That would make more sense with the variables from this problem. But I would, of course, accept that just fine with the x and the y. One other that I think I've marked before we do supply and demand, look at 46, which gives us another example of a piecewise function. 46. Says the percentage of obese children aged 12 to 19 in the U.S. is approximated by this function. P of t is 0.04t plus 4.6 and negative 0.005 t squared plus 0.945 t minus 3.4. The first branch, the first piece of it is good for t between 0 and 2. No, it's good for 0 and 10. If t is between 0 and 10, better. And that is far bigger than there. And this piece is good for 10 up to 30, including both. Okay. T is in years with t equals 0 being 1970. Okay. The first question is, what was the percentage of obese children at the beginning of 1970? So that means 1970 is year 0. Which piece would I put that into? First one. What is that if I plug 0 in? 4.6%. Not bad. That's good. Then it asked me for, at the beginning of 1985, what's t going to be? Yes. Which piece would 15 go into? 15 is in this interval, right? So I would have to put it into this piece. Okay. I think we would probably want to use our calculator for that. You could put that in line Y1 and use your table if you would like. I won't make you do that if you don't want to. If you got it, I'll take it in a second. Say that again.
8.51%.
8.51. Sound good? Good. You've still got it in there. They also said in the beginning of 2000. What year would that be? That's year 30. Use that in your table. Of course, that would also be in the second one because 30 is in the second piece also. What did you get for that one to 2 decimal places?
15.9091.
15 point. Wow. Wow. What is that saying? Over time, what's happening?
Eating
Too
more
much McDonald's.
cheeseburgers.
Yeah, it's increasing, so to speak, right? So, 1970, 85, and 2000. Okay. All right. That wasn't too bad, was it? That's just using a piecewise function. If they asked you to graph that, that would be a little tricky with the two-sided inequalities, but you could do it. What you would have to do maybe is put this in parentheses and then do it again with the t minus t less than 10 in parentheses, and it would show it. But I probably wouldn't ask you to graph one of those with the compound inequalities. Okay? But that's a good question. And last but not least is, and I'm going to go over here and actually move it. So it doesn't do like it's going to do. If, let's define the supply and demand functions. Supply function, P equals S of X. P is the price per unit at which the manufacturer will supply X units. Okay? The manufacturer wants to supply more units for a higher price, so it's an increasing function. Okay? So you might see it look something like this. The supply function, if I were to draw one. What if the supply function looks something like this? S of x. An increasing function. And then the demand function, P equals D of x. P is the price per unit that a consumer will pay for x units. And we know, and this should be total. That makes me so angry.
Might be able to go on the other side. That's what's going on.
Let me see if that would help.
And the large in the middle.
It doesn't like me.
Yeah, grab the bar and drag it
Yeah,
right there. Yeah, there you go. There we go.
that's better. Good. All right. Thanks for the help. It's never done that until this semester. It's crazy. Maybe it's just getting old, like me, right? Okay. So look what that says. The demand function, the consumer wants to purchase more units at a lower price. We know that, right? They want to purchase more for a lower price. So if P is your y-axis, for a lower price, the x would be larger, wouldn't it? So that would look like this. Your demand function could look something like this. Okay. And we're going to be interested where they meet, and we're going to call that point of equilibrium. And I don't have to move it again. Okay. Equilibrium price, price at which S of x equals D of x. Okay? Price at which every item supplied is bought. Okay? So basically, what they want you to do, if you can set your price to the equilibrium price, that's going to be optimal. All right? If you can agree on the price where the supply meets the demand, you'll sell every unit and not have an overage or an underage. And that would be ideal. And I think I say that at the very bottom. Theoretically, selling price equals equilibrium price. So, okay? I thought we would just try one. Look at number 68. Look at 68. One of these. '68 says, this is about tires. The demand function for tires is, no, this is about tents. 68 is tents. The demand function for tents is P equals negative 0.1x squared minus x plus 40. And the supply function is 0.1x squared plus 2x plus 20. All right? This was demand, and this was supply. All right? They asked me to find the equilibrium quantity and price. All right? So I want to find the x and p values where they meet, in other words. We could do that algebraically, but that would probably be a tough quadratic to solve, or we could do it with our calculator, which I bet you would prefer, wouldn't you? So if we do that, why don't we say y equals, let's put those in, negative 0.1 x squared minus x plus 40. 0.1 x squared plus 2x plus 20. All right. My only concern is so I can see those, I need to set the window so that I can see both graphs pretty well. Well, let's think about it. If they're talking about supplies of tents and price in dollars, what if we said, I know that the tents, I won't have negative tents. So what if we said 0, We'll say up to 100 just for, that might be shooting too far, but maybe 50. Let's start with 50. Probably wouldn't have negative price unless they're going to give it away, pay you for it. 0 up to, you think $100? Let's see if that shows me anything. I can see the intersection, but I way overshot the X, didn't I? I should go back to my X window and not go up to 50. How about 20, 30, 25? Is that better? Not bad. Okay. How do I find where they meet?
Intersection.
Second calc, intersect number 5. They'll say first curve, that's the first curve. Second curve, yes. Guess. You can get a little closer if you want to. Wow. So the equilibrium quantity is 5/10. And what's the equilibrium price? $32.50. So that's a cheap 10, isn't it? And they're not selling very many of them, are they? So,
Is it worth producing?
yeah. So, wow. I bet that's a small 10, very small 10.
They said 5 by 7, so. it's
5 by
pretty
7,
small.
very small, yes. Okay. Very good. So do you think that if I gave you supply and demand functions, you could find the point of equilibrium? And you know, if these were not quadratics, if these were just linear, it would be easy just to set them equal and do it on paper. Don't you agree? You could solve that. Okay. Very good. So the ones I would like you to try from this set, page 85. How about 1 through 17 odd, 19 through 35 every other odd, and then end up with 47, 65, and 69. Those are the only ones that I'm interested in. The rest of them are repetitive, or I'm not going to concern you with them. Okay. Now, this actually leads us up to where we actually start the new material. 2.4, we're going to define limits. And that's where I had wanted to get, so that we might not have to rush toward the end. So, raise your hand if you've ever studied limits before. A few of you have. Okay? So, let's define. Let me go ahead and clear these out. Let's see. Good. All right. And I will move that up at the computer for just a bit. Let's see. L is the limit of the function y equal f of x as x approaches the number a. If f of x values approach the unique number L as x approaches a from either direction along the x-axis. Okay. All right. If the values of f of x do not approach a unique real number as x approaches a, then the limit does not exist. All right. So there's our definition for limit. Let me tell you exactly what that's going to mean. Okay. What if I said this? And I think they give the first few as graphs, so I'm going to give you one too. What if I gave you this graph? Okay. What if I said it looks like this? See here. What if I asked you, what is the limit as x approaches 2 of f of x? This is what I want. As the x values get closer and closer to 2 from either side, where does the y go?
3,
Ah,
3.5.
if I get closer and closer and closer to 2 on the x-axis, the y gets closer and closer and closer to 3, doesn't it? If I approach from this direction, from the right-hand side, if I get closer and closer and closer to 2, the y value also goes up to 3. So that limit is 3. Does that make sense? As my x gets closer to this number, there's 2. The y gets closer to 3. Have to look at both sides. If I gave you this one, you know how sometimes we were doing piecewise functions? What if you graphed a piecewise function on your calculator? And it looked like this. What if this piece was like this, with an open circle there, and then the other piece looked like this? What if that was my function, and I asked you this question? What is the limit as x approaches 1 of f of x? From the left-hand side, if I get closer and closer to 1, where does it look like it's going? It looks like it's going up to 3, right? If I get closer and closer to 1 on the x-axis, the y value gets closer and closer to that 3, that open circle. But if I come from the right-hand side, if I get closer and closer and closer to 1, it's dropping down to where? 4. Well, this left-hand limit does not equal the right-hand limit. So you know what I say? This limit does not exist. Okay. And that would be my answer. This one was great. If I approached 2 from either side, the y values both went to that 3, didn't they? But if I approached from the left, it went to 3. From the right, it went up to 4. They are not the same, so that limit does not exist.
So can you only have one limit?
Yes, one limit. But in the next section, and I don't want to jump ahead, but later, if I said this, what if x approaches 1 from the right? You would say the answer is 4. Or if I didn't put a plus here, but I put a minus, approach from the left, you would say 3, wouldn't you? So that would be a one-sided limit. We do that in the next section, not this one. But for this limit to exist, you have to approach that number a from either side on the x-axis, and it has to go to the same number. And that would exist and be that number, that y value. Does that make sense? They give you a few. Do you see on page 111? From 1 to 8, they give you some graphs. Okay? This is the question in number 2. Very similar to the ones I just did. Number 2 says find the limit as x approaches this number a. Well, a, they say, is 1 in number 2. You see that at the bottom? A is 1 of f of x. Tell me, if you approach that 1 on the x-axis from either side, where does the y go? That's easy, isn't it? It's great. That limit's 2. What would you say about number 4 if I said, what's the limit as x approaches that number a, which is also 1 for this one? Does not exist because the left-hand limit looks like it's going to 1.5, but where's it going from the right? 3. They're not equal. So that limit, I'm just going to say DNE does not exist. Okay. 6 is an interesting one. Does everybody see number 6? This is the question for number 6. What is the limit as x approaches -2 of f of x. If you get closer and closer to -2, what do both sides go toward? They go to that open circle where 3 is. Do you agree? But see, that's great. That is the limit. The limit is 3. But what's funny is that if you actually said what is f of -2, f of -2 is actually 4 where the closed dot is. Do you see that? So the limit is 3. That's what both sides approach, that open circle. But the value f of -2 is actually 4 where the closed dot is. That's going to be important later, but right now all I need you to know, that limit exists and it's 3. It approaches that open dot. Okay? What would you tell me about the limit in number 8 as x approaches 0? All right. If you get close to 0 from either side, from the left, it goes to 1. From the right, it goes to infinity. It keeps going up forever, doesn't it? What do I say? D and E. Very good. Like it. All right. Turn the page to 112. Do you feel pretty comfortable with those if I gave you a graph and said what's the limit as x approaches a certain number? Okay. Very good. Do you see from 17 to 22, they give you piecewise again, don't they? Why don't we look at 18? Eighteen gives me f of x equals x minus 1 if x is less than or equal to 3 and -2x plus 8 if x is greater than 3. All right? This is what the question is. What's the limit as x approaches 3 of f of x? They want me to graph it and look graphically like we did on those first ones. But I want to estimate what it is before we graph it. Tell me this. If x gets very close to 3 here, if it's like 2.99999, if that gets close to 3, what's that value? About 2, isn't it? Well, what if I come from above? 3.00001. If this is very close to 3, what's that?
2.
So what's your guess? What do you think that limit is?
2.
I think it's 2. We could prove that by looking at the graph. Let's try to graph that. That's another good practice for a piecewise on our calculator. If we graph that, remember I'm going to put in parentheses the first piece. That is x minus 1. And that's good for x is less than or equal to 3. X, remember it's second test. Less than or equal to is 6. Okay. And I'm going to drop down to line y2 to put the other piece. That is -2x plus 8 in parentheses. 2x plus 8. And put in parentheses x is less than, which is 5. X is less than 3. Okay. I'm going to go back to a standard window and hope I can see it.
Isn't it supposed to be greater than 3, not less than 3?
Oh, thank you. Second. You shouldn't talk and punch buttons at the same time. Greater than 3. Thank you. Very good. If I graph that, just zoom 6, standard window, zoom 6. There's the first piece. There's the second piece. If I get close to 3, here's 3, from either side, what's it going up to on the y-axis? It's going up to 2, isn't it? You see it better here. If I get close to 3 from either side, the y value it goes up to is 2. So that was my limit. That's not a hard concept, is it? Has to be from both sides, though, for it to exist. Okay? Very good. Let's see. How about 22? Says f of x is absolute value of x minus 1 if x is not 1 and 0 if x is 1. They want me to find the limit as x approaches 1 of f of x. Well, would you agree with me? And I think if you remember your college algebra, you could do this even without your calculator. What is the graph of just plain old absolute value of x?
V.
Isn't it the v at the origin?
You screwed it down.
How would that be different? Would it move it up, down, left, or right if you put minus 1 inside?
Right.
Good. All right. So instead of having the v at the origin, I'm going to have that v touching at 1, right? There's my graph. Okay. Now they said that's good for every value except 1. But if x is 1, y is 0. So that closed dot would fill in the hole that was at the corner there, wouldn't it? Okay. What do you tell me if I get closer and closer to 1 from both sides? Does it go to the same place?
0.
Yes. It goes to 0, doesn't it? If I get closer and closer and closer to 1, that goes down to 0, doesn't it? Closer and closer and closer to 1 from the left goes to 0. So that's my limit. The best you could do to graph that on your calculator is just to do this piece and know that there's an open circle here, and this closes in that circle. If x is 1, y is 0. So, okay? So it looks just like that. All right. Now, why don't we try a few where they just give us some expressions to find limits of? I want you to tell me just intuitively what you think this would be. This is 24. If x gets closer to -2, I don't see an x to plug in. So what's the limit? Think of it like this. What is the graph of y equals -3 if there's no variable? Isn't it a horizontal line down there? So if I get close to -2 on the x-axis, if I get closer and closer and closer to -2 from either side, what's the y value? That makes perfect sense, doesn't it? So the limit of a constant is just that constant. Because there's no x to plug in for, is there? All right. What would you say about 28? The limit as x approaches 3 of 4x squared minus 2x plus 1. Or 4t squared, excuse me. These are t's. T squared minus 2t plus 1. Okay. I could sketch that. We could graph it. It would be an upward thin parabola, remember from college algebra? But as t gets close to 3 from either side, that's an unbroken curve. It's going to go to the same place, isn't it? If it's a polynomial like this, you could just plug the 3 right in, and that's your limit. So what would that be? 9 times 4 is 36 minus, limit would be 31. No problem there. So if it's just a plain old polynomial, I can just plug that x value or t value right in and get my limit. That's nice. Okay. Same type thing for 34. What if you're given that one? I don't think you would have a problem there either. The limit as x gets close to 1 of x cubed plus 1 over 2x cubed plus 2. What does that give you? 1/2? I like it. If I plug 2 over 4 would reduce to 1/2, that's good. You know what would be even nicer, and this would be useful in other problems maybe? You could just plug the 1 in and get 2/4 reduced to 1/2. What if I factored it? What if I said x cubed plus 1 over 2 x cubed plus 1? What happens?
Yeah.
Those just cancel right out, don't they? And that leaves me with 1/2. The constant. Isn't that nice? Okay. But you could have plugged the 1 right in, you get 2/4, it reduces to 1/2. Let's see. Similar ones down to 40, not much trouble there. What I do want to mention to you, for ones like 41 through 48, I would refer you to page 102. And I've put that in my notes also. These are the properties of limits. If you ever want to look at those, okay? What they say, like the first property on page 102 in that box, says that if you have the limit of a function to some power r, just find the limit of f of x and then raise that answer to the r power. You'll get the same thing. The second property says if you have c times a function and you're taking the limit, you can bring the c outside and multiply at the end after you take the limit of just f of x. That makes good sense, doesn't it? Is that okay? If you're adding or subtracting functions, take the limit separately and add or subtract the answers. That'll work. That's number 3. Same thing for product in number 4. And what did they say in number 5 for the quotient? You can take them numerator, limit, denominator, but m cannot be 0. Of course, because you can't have an undefined. So those are your properties for limits. So would you agree that if I asked you to do 44, and you already know from the instructions what the limit of f of x and the limit of g of x are, wouldn't I just multiply those? 3 times 4 would be 12. Okay? Using that property. Because they give you the limit of f and the limit of g in the instructions above 41. That would be good. These are the ones where we have to start really thinking about things. And let me go ahead and show you that. I think I've written it in the notes. I went ahead and said properties are on page 102. Let's see. In a few minutes, I don't think in the next few though, we might have limits that approach infinity instead of a certain value like 2 or 3. What if it's x approaches infinity? We'll have to look at some of those. Or x approaches negative infinity, where x decreases without bound. I'll show you some of those soon. This is what I really wanted you to see though. Limits that have indeterminate form 0 over 0 must be evaluated strategically. That doesn't tell you a lot, does it? Basically what I mean by that is let's use algebra like I did in this one. You see how I factored and canceled and made it 1/2 and it was very easy? For instance, look at number 50. That's a perfect example. Number 50 says, find the limit as x approaches negative 2, x squared minus 4 or x plus 2. Well, I'm in trouble because if I plug negative 2 in like we love to do in those last few, what do I get? I get 0 over 0, indeterminate form. But you all know how to factor that numerator, right? How can I factor that numerator? Exactly. What can I do there? Cancel. Now that just leaves me x minus 2. Now tell me what the limit is. If x gets close to negative 2, my answer, you're right, negative 4. No more indeterminate. So anytime you get 0 over 0, you've got to do some algebra on that to try to manipulate it so you don't have that anymore. Okay? But I have a lot of people in previous semesters, they'll get this and they'll tell you, oh, it's 0 over 0. Well, that's not good enough. That doesn't tell you. But what's interesting is if you graph this on your calculator, you know what it graphs? Y equals x minus 2. But there is a hole at negative 2 that your calculator doesn't show. So it would be a line on your calculator. If I graphed x minus 2, that would be, 20? And 0, negative 2. So here's my line. If I graph this, I think I would see this. But at x equal negative 2, I'm going to have a hole down here. I'm going to have an open circle. So at negative 2, negative 4, I would have that. That would be the graph of it. If you graph this, it's this whole straight line except an open dot there, because if I put negative 2 in for x, it is 0 to 9. It reduces just to y equal x minus 2. Doesn't it? Good. And would you agree that if x gets close to negative 2 from either side, doesn't it go down to negative 4? That's the limit, isn't it, from graphically looking at it? Okay. If my graph were to look better. Okay. All right. But you see what we had to do? We had to factor and cancel so we could actually find the limit. What could you do on 52? See if you can find that limit. While you look at 52, let me make sure we're all here. I'll call the roll. Let's see. Brian, I think, was Brian? Brian is here. Alicia. Lexia. Trevor is the one who had car trouble. He called. Let's see. Rachel is here. Rachel King is here. And Jordan's here. Caleb is here. Justin McGuire. Not here. Leo is here. Justin's here. And Marie is here. And Renita's here. Elizabeth is here. Catherine's here. Brandy is here. Very good. Right. Did most of you factor in x out of the numerator? X times 2x minus 3, which allowed that x to cancel. So what's that limit if you get close to 0? These are not hard, are they? These are not very hard. Okay. The tricky part, and I won't make you do this right now, but the tricky part about 58 is you have to factor the numerator with that formula from intermediate algebra where you factor difference of cubes. I would not make you know that by heart. I would give you that formula if I gave that to you. And in 60, you have to do what they give in the hint. 60 says x minus 4 over square root of x minus 2, and they want to find the limit as x approaches 4. Well, you know if I plug 4 in, I've got an indeterminate form. But what the hint in number 60 says is try to multiply by the conjugate of that radical expression. So what if I multiply by square root of x plus 2, top and bottom? Okay. If I do that, I'm going to leave the numerator alone. X minus 4 square root of x plus 2. What would the denominator be? Those are conjugates. This would be square root of x squared, which is x. The outer and inner would cancel. And what are you left with at the end? What happens? What's my limit going to be? Yeah, if I plug 4 in there, square root of 4 is 2 plus 2, so that limit is 4. Isn't that great? Nice. Would you have thought of that if they didn't give a hint, though? Maybe not. Maybe you would. Very good. Okay. What if we say that we will do the limits as x approaches infinity next week? This is good enough to start? Okay? I don't want to overwhelm you. Why don't we say for now, the assignment so far in this section, what if I said 1 through 7 odd, this is page 111, 1 through 7 odd, and 17 through 61. And I think I'm saying odd for now. And we'll finish up next Wednesday after the holiday. So I appreciate you letting me go ahead with the notes so we don't feel stressed at the end. Do a good job on that quiz. You've got a whole week to do it. If there's any question, you can stop by and see me. I might give you a hint on it. But I will take that up next Wednesday at the beginning of class. And have a good week. I'll see you next week.